Welcome back. In this video, we are going to solve exercises 9 to 12 of chapter 1. And they're a little bit easier than the exercise of the previous video. And they could constitute easily a question in the exam. Okay, so exercise 9 is an extension of exercise 3, if you like. But in exercise 3, we had the union of the closure of two sets A and B. Here we have the union of the closure of a collection. So we have a collection now, A lambda, of subsets of a metric space. We have to show that the union of their closures is contained in the closure of the union, and you have to give an example where equality fails. Okay, this is easy, because the idea to prove the first, to prove the inclusion was used in exercise 3. Because which one is bigger, A lambda, pick a one lambda. Which one is bigger, A lambda or the union? The union is bigger. So by exercise 3, the closure of A lambda is contained in the closure of the union. But this is true for every lambda. There's no restriction on lambda here. So the union of A lambda bar is contained in the closure of the union in the same set. So straightforward. Now for a counterexample, just take L equal the set n star, the set of positive integers, and take the interval an to be the open interval 1 over n, 1 minus 1 over n, and see what happens. What's that? An bar is the closed interval 1 over n, 1 minus 1 over n. And you probably know that the union of all these closed sets is the open interval 0, 1. Whereas the closure of the union is the closed interval 0, 1. Okay, so just write the details, because it's very important that you take a paper and a pen and train yourself to write correct proofs. Okay, so you cannot learn just by watching videos. Okay, so this could be easily a question in the exam. You have to come up with counterexamples, examples and counterexamples. Exercise 10, very similar, but with intersection. The interior of the intersection is contained in the intersection of the interiors, and equality may fail. So once again, the intersection is contained in each A lambda. So the interior of the intersection is contained in the interior of A lambda, but this is true for every lambda, therefore it's contained in the intersection of the interior. So pretty straightforward. Okay, counterexample. Take, for example, the increasing sequence, the decreasing sequence, minus 1 over n, 1 over n. And see what's happened, what's that and what's that. Okay. The intersection of an circle, or an, same thing actually, because the intersection of an is the same as the intersection of an circle, which is actually the singleton 0. Okay. So this is here the singleton 0, but the interior of the singleton 0 is empty. So this is empty and this is the singleton 0. Okay, also could be a question in the exam. Now, before we move to the next exercise, let me just rephrase or formulate a consequence of proposition 1.2 in the lectures that states that the intersection of two closed sets is a closed set, and the union of two closed sets is a closed set. Okay, just this is a particular case actually. So if you have two subsets A and B of a metric space, if A is open and B is closed, then A without B is open. So in words, when we remove a closed set from an open set, we get an open set. And if A is closed and B is open, then A without B is closed. We don't need actually to have B contained in A or A. So because A intersected with B is by definition the set of elements in A which are not in B. So it's A intersected with the complement of B. So this is just, so we write, so this is by definition, A without B is A intersected with the complement of B. It's the set of all elements in A that are not in B. Now, In 1, if A is open and B is closed, then X without B is open. So we have an intersection of two open sets, and the result is open. Okay. And now, if A is closed and B is open, the complement of B is closed, and you get an intersection of two closed sets, so it's closed. Okay, so it's very easy. Okay, now I'm saying that because it's useful actually. So now we have to prove that in a metric space, the closure of the complement is the complement of the interior and vice versa. Okay, well, actually we can deduce A from B and B from A. Now, how do we prove that? Double inclusion. Okay, so look, if you look at X without a circle, okay, a circle is an open set. Therefore, we know that because by definition it's the biggest open set contained in A. Therefore, the complement is closed. Now, which one is bigger, a circle or A? A is bigger than a circle. So a circle is contained in A. So the complement of A circles contains the complement of A. So we have to reverse when you do when you take complements, you reverse the order. Okay, so this is bigger than this. And so now this is a closed set containing that, and by definition, the closure, so it contains the closure because the closure is the smallest closed set containing that. Okay, so here we have X without A contained in X without a circle, and so the closure of this is contained in that. So we have one way. This is easy. Now, for the converse, we pick an element X here, so not in a circle. We have to prove that it's here, and it's easy to use proposition 1.8. So if X is in the complement of a circle, it's not in a circle. What does it mean that X is not in a circle? What does it mean that X is in a circle? It means that there is an open set containing X and contained in A, right? So if X is not in a circle, this means that no open set containing X or no neighborhood of X is totally contained in A, right? So no neighborhood of X is contained in A. Therefore, every neighborhood of A necessarily meets the complement of A, just set theory. So any neighborhood, you can take an open neighborhood, doesn't matter actually, okay? So if you take a neighborhood of X, it cannot be contained totally in a circle because otherwise we would have X is contained in a circle, just reason by contradiction, if you like. So there is an element in A, in U, so if you to call this neighborhood U, so there is an element in U not in a circle. Not in A, actually. Okay. So therefore, this element is in the complement of A. Okay. So by proposition 1.8, X is in the closure of X without A, and therefore we have the reverse inclusion. Okay. So it's easy, but if it's your first time, I understand that in the first course of topology, it may seem a little bit difficult because you don't know where to start. But the purpose of the exercises is to give you enough confidence, and enough ideas to start with. Okay, and you will get used to that, to this kind of reasoning. Okay, now, and okay, we can also express the same idea as follows. We reason by contradiction. Okay, so if you want to prove that, so we have this. To prove the reversed inclusion, we prove that if X is not here, then it's not here. So same thing, by contraposition, if you like, or by contradiction, same thing. So maybe this is a little bit easier to you to understand. If X is not in the closure of A, then by proposition 1.8, there exists a neighborhood of X not meeting X without A. Okay, so there exists a neighborhood. Take it to be open. Doesn't matter. So U doesn't intersect the complement of A. What does it mean that U doesn't intersect A? It means that if Y is in U, then Y cannot be here. If it's not in the complement of A, then necessarily it's in A. So set theory tells us that U is contained in A. So if U is contained in A and U is open, then U is contained in a circle. And since X is in U, then X is in a circle. So maybe this is a little bit easier, but it's the same idea actually. Okay. Now, B can be deduced from A just apply A, but instead of A put B. So X without B, the closure of X without B is X without B circle. And now take A to be X without B and see what happens. I will let you write this because this is just an exercise in set theory. So, and of course you can repeat the reasoning here actually, if you like. You do it, but you don't need to repeat everything because you can deduce it. Of course, we can prove first B and then deduce A, if you like. Okay, now last exercise also could be an examination question. We have two subsets of a metric space. So A and B are two subsets of a metric space. We have to show that if A is open, then A intersected with B bar is contained in the closure of A intersected with B, and we have to give an example where the inclusion is the first question. Now, this is easy. How do I prove that? The easiest thing to do is to take an element here and prove that it's here, because we have proposition 1.8 that tells us when a point belongs to the closure. So take a point in A intersected with B bar. So first, this means that X in A and X in B bar. What does it mean that X is in B bar? It means that by proposition 1.8, every neighborhood or every open neighborhood of X meets B. Okay, now, since A is open, then O intersected with A is also open. Okay, so it's a neighborhood of X, just an open set containing X. Now, I take this, instead of taking O, I take O intersected with A. So this, since X is in B bar, this set must meet B by proposition 1.8. Now, how can I rewrite that? I can write that as by the associativity of the intersection. I can write that as O intersected with the intersection of A and B. So, but O was arbitrary. So every neighborhood of X meets A without B. So by proposition 1.8, again, X is in the closure of A intersected with B. So straightforward. Now, counterexample, you write the details. Take A to be the interval, the open interval 0, 2, and B to be the closed interval 1, 3. It doesn't matter. You can take open interval 1, 3. It doesn't matter, or semi-closed. Okay, what happens here? What is A intersected with B bar and what is A intersected with B? You tell me. You write the details, but this is a counterexample. Okay, so here we took something that two overlapping sets. Okay, their intersection is not empty. Because of course, if the intersection is empty, then we have equality. Okay. If A intersected with B is empty, this is empty and this is empty. Okay. Now, second question, we suppose that A and B are open. We have to prove that these three conditions, A doesn't meet B, A doesn't meet B bar, and A bar doesn't meet B, are equivalent. Of course, since B bar contains B and A bar contains A, then 2 implies 1, of course, because this is bigger than this. So if the big one is empty, the small one is empty. And same thing, this A bar contains A, so if the bigger one is empty, the small one. So the interesting thing is the converse. So if A intersected with B is empty and both A and B are open, then we have 2 and 3. They are actually symmetric. So we reason by contradiction. Suppose that 1 holds, but B does not hold. The 2 does not hold. Okay, so take an element in the intersection. Okay, so X is in A and X is in B bar. Since A is an open set and contains X, then A is a neighborhood of X. But since X is in B bar, A must meet B. Contradiction by proposition 1.8. So this is impossible. So 1 implies 2. And similarly, by symmetry, actually, because A and B play the same role, 1 implies 3. Okay, just change the roles of A and B. Okay, so this concludes exercise 12 and this third video on the exercises of chapter 1. Thank you for your attention and see you next time.